I'm making a few videos about error correcting codes, mainly so that when a few weeks from now I've totally forgotten what little I know about error correcting codes, I'll be able to go over these videos again and refresh my memory. But what I'm interested in is parity codes, error correcting codes that are going to be of use in radio communication, and in particular in the RF Bitbanger, which is a software-defined radio that I recently built, and which I can modify the software of and play with. And I want to have some record of how these error correcting codes work in a software-defined radio. And they're going to be generating code words and also decoding received code words using matrix multiplication. And so that's what we're going to focus on here. But first of all, let's just think about what a Hamming code word looks like. This is an example here. The 7-bit code word from a Hamming 743 code word has 3 parity bits, which are in the first, second, and fourth position. And then the message bits, the message that you're actually going to be sending, those bits are stored in positions 3, 5, 6, and 7. Okay, so 1, 2, and 4 parity bits, 3, 5, 6, 7 message bits. Okay, and how do we get the parity bits? How do we figure out what they are? They're just represented by question marks up here. But Hamming's clever idea was to look at the labels of the positions of the bits in the message bits that are in the code word, and think about their binary expansion. Okay, the expansion of 7 binary expansion is 1, 1, 1. It's 4 plus 2 plus 1. Okay, the expansion of 6 is 1, 1, 0. 4 plus 2 plus 0 is 6. And on down to 3 here. 3 is, there's no 4 in it, just a 2 and a 1, and that's 3. Okay, and so that tells us which message bits we should associate with parity bit that's going to be in position 1. Okay, so it's going to be the parity bit for the bits whose label has a binary expansion with a 1 in it. Okay, so this label has a 1 in its expansion. This label has a 1 in its expansion. There's no 1 in the binary expansion of 6. That's a 0. But there is in the expansion of 7. Okay, and so parity bit number 1 is going to be the parity bit for these 3 message bits, the ones with 1 in their expansion of the label here. That's bits 3, 5, and 7. Okay, so we're going to add together the bits 3, 5, and 7 modulo 2, and then the parity bit here is going to be whatever we have to add to that to get a 0. Okay, and so let's just do this one right here. The parity bit for the first parity bit that's going to be in position 1 is going to be created by adding together the message bits located at 3, 5, and 7, and so that's 0, 1, and 1. Well, 0, 1, and 1 adds up to 2, which is 0 modulo 2. Okay, so that's going to be our parity bit here. That's a 0, and then we need to do these two the same way to come up with them. Okay, and so ultimately what we wind up with here is this code word, 1111. Well, 111 here for the first 3 message bits and a 0 for the last message bit, but parity bits of 1 and 0 and 0. Okay, now that's great, and that's what the original Hamming codes look like. The message bits and the parity bits are interwoven, because all of the powers of 2 are going to be parity bits. But it's going to be more convenient for us in our software-defined radio programming if we use systematic code words, where we have all of the bits that are from the message together, usually at the start of a code word, and then the parity bits are together at the end. So here that just requires flipping bits 3 and 4. Okay, and we're going to keep their labels, so their labels are now going to be out of order. Okay, that's so that we can remind ourselves of how we get the values for the parity bits. But so whichever one we use, since our messages are of length 4, the message itself has 4 bits in it, there are only 16 possible binary messages of length 4, okay? 2 to the 4th power. And so here are the 16 code words that the original Hamming code would have, okay, in them. The corresponding 16 code words with bits 3 and 4 flipped are over here, and that's called a systematic code. Systematic code has all of the message bits at the front and the parity bits at the end. Okay. Now looking at the systematic code and just looking at the first 4 bits here from the message, we can recognize that some of these bits could be used as some of these message words could be used as a basis for a little 16 vector space. Because if we have this message here that is 1 0 0 0, and then another one that's 0 1 0 0, and another one that's 0 0 1 0. Which is 0010 right here, and another one that's 0001, then we have something you can recognize as a identity matrix, and also a basis for a little vector space here over these 16 longer vectors, code word vectors. Okay, and so it's natural to just copy these and paste them into a matrix, and when we multiply the message vector here, this row vector, by a column vector in the basis, it's a dot product, so it's component times corresponding component, and then everything added together, but added together modulo 2. Okay, then what we're going to get from the identity portion of this matrix is the code word itself. It's going to appear. The message itself is going to appear as the first 4 bits of the code word. Sorry. Okay. Then what you get in the last 3 bits are the parity bits that correspond to them, because of the way that we created the code words in the first place. So, and then it's important to realize that any other message here can be gotten by adding together 2 or more of the basis code words here. And so that's what makes this matrix multiplication work. Now, you may say, well, why not just use a lookup table? I mean, if you receive a code word, it might have 1 error in it. Okay, just find which of the 16 code words it's closest to, and then you've got your corrected code word. And you're absolutely right if you think that if you were actually coding something in a software-defined radio to use the Hamming code, it would make a lot of sense to just have a lookup table with these 16 values in it stored in memory, and then just calculate the Hamming distance of your received message to each of these and pick the one that's closest. And that's fine, except our actual error correcting code we're going to be using with the RF bitbanger, quite a bit more complicated. The code words are of length 24. Okay, and there are 12 message bits in each one of those code words. So there are 2 to the 12th of them, which I think is 4096, something like that. And our microcontroller that's going to be running the software-defined radio is an Arduino Uno. Okay, the Arduino Uno does not have a lot of memory space for storing tables and for doing all the calculations involved in calculating the Hamming distance to each one of those code words. And so much simpler is to just use this matrix multiplication. And we can make it even simpler than that, because if we go down here and think about it, whoever is using the RF bitbanger to transmit a message is typing in a single character like the letter A, and it's going to be associated with some binary number like we have here. Okay, so we've got the message, all right, in our transmitter. It's been entered in using a keyboard, say. All we have to do is multiply that times this portion of the generator matrix to get the parity bits. And then all we have to do is glue together the message and the parity bits by just reading them into a single array. And then you're ready to start transmitting that code word. So quite simple setup here with matrix multiplication and not requiring the memory or computing power that a lookup table would. Okay, and so, all right, once you have your code word, you're going to be transmitting it through some channel, whether you're transmitting with the RF bit banger, you're transmitting electromagnetic waves through the atmosphere, or inside a computer, the CPU could be sending a message to the hard drive to retrieve certain bits of data, and then the hard drive is going to be transmitting it back to the CPU, and constant conversation going back and forth, and you don't want errors creeping into that. Now, errors are not going to be very frequent in that environment, so Hamming code is a natural for that. You're probably not going to have anywhere near one error per code word, per letter of the alphabet, or byte of any sort that's being sent. So yeah, these codes work great for that, and codes were in use that had way more data length than our 4-bit data length, but still can only correct one error. Though that was fine because the errors weren't that frequent inside the desktop computer. Okay, but being transmitted over the air, we're going to have longer code and more possibilities for error. So definitely, this is something to be concerned about, is correcting errors. But so here in our simulation, our error vector E, if there's no error introduced into the code word, is just going to be a long, 7-bit long 0. Okay, if we make any of these a 1, that means we're going to flip the corresponding bit in the transmitted code word and wind up with an incorrect code word here. Okay, so I'm going to flip bit number 3 here. I'm saying that the channel that's carrying this transmission corrupted this bit, turned it from a 0 to a 1, and so our received code word has all these 1s in it and 2 zeros at the end. Okay, now how are we going to correct that using the parity bits? Well, we're going to multiply our received code word R, okay, by this parity check matrix, okay, which I've already set up for parity bits 4 and 2, but to just show you how simple it is to set that up, we'll look at the case of parity bit number 1. Now this is reminding us here that 1 is a parity bit for bits that are labeled 3, 5, and 7, okay, and so we're going to put a 1 in for the label of the parity bit itself, 1, and then 3, 5, and 7, and put zeros in everywhere else. Okay, and now our multiplication can happen, and the product is called the syndrome. And the syndrome, if it's all zeros, means that there was no error. We received one of the official code words, one of the official 16 code words, which this determines by giving a product of 0, 0, 0, 0 here. If that's not correct, if we did have a bit flipped, then the syndrome is in binary. It's representing the position of the error. The error was in position number 3 here, and this is binary for 3. Okay, so easy in software to then use this value, go back and flip the bit, in this case the bit labeled number 3 here, and give the corrected code word, which has our original message of 1110 instead of 1111. Okay, so that's error correction going on here. And next we'll talk about the extended Hamming code, because we're going to be using the extended Golay code. And so what is this extension for? And we've already gone 14 minutes or a little over that, so we'll save that for the next video.